Press continue. Hi, welcome to everybody, both in-house and out of the house. Today is one of the first lectures in the joint BARC MIAO series on computational complexity. Our guest today is Nutan Limaye, who joined ITU just a few weeks or months ago. And we look forward to seeing this by now quite famous, amazing result, which is widely regarded as the best thing that happened to circuit complexity in 2021. And the year is almost over, so I think you win that contest. Over to Nutan.
So for the live audience, is this visible?
I think maybe there's a blackboard line on.
Yeah, exactly. So should we be able to switch that off?
Has your Danish course already included the tavlelys? Because that is the word for blackboard light.
Or we'll just leave it if it's okay, because this has worked out now.
But how about some of the curtains?
Yeah, maybe.
It just looks like it comes from the roof.
Okay.
I found the towel. It's double.
It's better.
Oh, yeah. Okay. Do you also want one of the curtains down? It's
Definitely.
Okay. Okay, so I think I'll start because some people have something at 3, so let's start. Thank you for having me. Thank you, Jakob, for inviting me for this talk. Thanks, Thor, for the generous introduction. So I'm going to talk about superpolynomial lower bounds against low depth algebraic circuits. I will try to not assume any prior knowledge and feel free to stop me anytime. The talk outline is as follows. I will tell you what algebraic circuits are. I'll try to motivate why one would want to prove lower bounds for constant depth algebraic circuits. Why is it interesting? Then I'll tell you about the result. The lower bound result also implies a couple of other results, so I'll talk about that. And then if time permits in the first half of this seminar, I'll tell you a little bit about the proof ideas. And I'll try to end with summary and open questions. So the proof ideas, we'll see if the time overshoots, we'll move everything to the second part. But I would like the early audience to know a little bit about the proof. So I'll try to see if I can do that. All right, so algebraic circuits are simple objects that compute polynomials. Polynomials are something that perhaps all of us know. They are just sum of monomials. Monomials are product of variables. And you could have coefficients coming from a field. And in general, we'll assume large fields of characteristics 0, unless specified otherwise. Algebraic circuit is like this object, which looks like a graph. It's a directed or cyclic graph. Its leaves are labeled with variables. And then you have gates. It could be a plus gate or a multiplication gate. A plus gate just takes the values computed at its children and adds them together. Multiplication gate just takes values computed at its children and multiplies them together. Eventually, you compute a polynomial, which is the output of the circuit. It's okay to assume that the circuits are layered with plus gates followed by multiplication gates followed by plus gates, because if there were 2 consecutive multiplication gates, you could just squeeze them together. And similarly for plus gates. So we can just assume without loss of generality that you have this alternation of layers. And in this case, for example, on the picture, we have a depth 3 algebraic circuit. We sometimes also refer to it as sigma pi sigma circuit, where sigma stands for the sum, pi stands for the product. And it's also okay to assume that the top gate is a multiplication gate, is a plus gate, because if it is not, if say the polynomial is factorizable, then you just put a false dummy plus gate at the top. So we just assume that the circuits just look like this, plus, multiply, etc. There are a couple of parameters about the circuit that are of interest to us that people usually consider. One is depth, the other is size. Depth is simply the length of the path from leaves to the output gate. And size is the number of operations in the circuit. So in this picture, we have a circuit of depth 3 and size 8. Okay, so that's algebraic circuits. That's all we need to know for now. So why do we study polynomials? Well, polynomials arise in many, many interesting places very naturally. For example, in linear algebra, you have determinant computations, or in matchings, graph matchings where determinants are important, and so on. So polynomials arise at unexpected places quite naturally. And when we try to compute a polynomial, there are a couple of things that are of interest. So look at this polynomial. It's a very simple polynomial. It just puts together, it takes all subsets of universe n and multiplies out the variables that are present in that set. Now, this circuit that I've drawn is a depth 2 circuit of size 2 to the n. But with a little bit of thought, you can see that the same polynomial can also be computed by this other circuit. Now, this circuit, for namesake, is sigma pi sigma circuit, because there's a trivial plus gate that I'll just add at the top for fun, and then a product and a plus, right? So, and now you'll see that the number of operations here is far fewer. It's just order n. And now this is the thing, that given a polynomial, it's not a priori clear that the way of computing it, what is the best way to compute it? And for some polynomials like this one, if you put in a little bit of thought, you might come up with much better representations for the polynomial. But for some others, after much thought, people have not been able to come up with better representations. And then one sits and thinks about why that is the case. And that's how lower bound questions arise. So when we study lower bounds, we are trying to ask what is the best way to compute a certain polynomial? What are the basic number of operations required to compute a polynomial? Now, why would one want to prove algebraic circuit lower bounds? Well, one reason is it's the dual to algorithmic thinking, right? So algorithmic thinking, we all like. As computer scientists, we want to come up with better and better algorithms for tasks that are important to us. And this is, clearly important. But then when there are times we cannot do that for certain problems after much effort, then the thought also comes to mind that why is that the case? Is there some inherent reason for the hardness? And from that point of view, it's interesting to ask lower bound questions just to understand why all of us together are not able to prove upper bounds. There's another reason, which is slightly complexity theoretic reason, which is if we decide to care about P versus NP question, then it's known that formally algebraic circuit lower bounds are like a stepping stone towards P versus NP. There's a result by Bergisa not too long ago, where it's known that if P can be separated from NP in the non-uniform setting, then in fact, that will also imply VP and VNP, which are the algebraic variants of P and NP, are separate. Which then means basically that proving lower bounds in the algebraic world is formally easy than perhaps solving the big P versus NP question. Also, there's no $1 million attached, so maybe it's possible. Then why do we want to prove constant depth algebraic lower bounds? And there are a couple of interesting reasons. One would wonder that, oh, these are constant depth circuits. What can they do? You should be able to prove a lower bound very easily because the model looks so restrictive. Depth 3 circuits, what can they do? Yeah. So then maybe lower bound question is kind of easy and should be solved by now. Well, there is a reason, a good formal reason to believe that depth 3 circuits already are quite powerful. So consider that there's a polynomial P on n variables of degree D, which can be computed by a polynomial-sized circuit of size, say, polynomial in the 2 parameters we have, n and d. Then it is known that such a circuit can be squeezed down to depth 4 without too much blow up in size. The blow up in size you would expect is like the non-trivial, the trivial upper bound is n to the d, because there are those many monomials in a polynomial of degree d on n variables. So you can even come up with a depth 2 circuit of this size. What this says is that if you're allowing depth 4, then you can get non-trivial savings on the size. You can get an upper bound of n to the order square root d. This is a beautiful set of results by Agrawal, Vinay, Khoran, and Sebastian Tavenas, one of our co-authors. In fact, more is known. Not only do we need to stop at depth 4, we can squeeze down the circuits all the way down to depth 3. Again, without too much blow up in size. Okay, here the characteristic has to be 0. So this kind of construction only works over large fields. But this result is also known. This is a result by Gupta, Kamath, Kayal, Saptarshi, and Sebastian again. Okay, so what this says, the story put together, is that actually constant depth circuits are reasonably powerful, at least in the algebraic world. So proving lower bounds here actually is interesting.
So far, no randomness is involved.
No randomness is involved. All these constructions are deterministic, quite simply, yeah, very, very beautiful upper bounds.
These are uniform.
These are uniform. Yeah, so very beautiful set of results just to motivate why depth 3 circuits or depth 4 circuit lower bounds are interesting, because they can actually do non-trivial stuff. There's yet another reason to care about such results, the one that relates to the P versus NP problem. So this P and NP we kind of know, but PP and VNP not everybody here would know. I won't define them right now. It's not important. They are just algebraic variants of P and NP. That's enough for our discussion. And what I just told you on the previous slide is that if the polynomial is in VP, VP you can think of as a placeholder for anything that is efficiently computable in the algebraic world, just like P is a placeholder for such things in the Boolean world. So if a polynomial is computable efficiently in the algebraic world, then it can be squeezed down to depth 3 with a size blow up of only n to the order square root d. This is what I told you on the previous slide. Well, now, if somebody comes up with a polynomial f in VNP, for which we are able to show an n to the little omega square root d lower bound, this is open, but if somebody is able to do this, then we would have separated VP from VNP, quite simply. Okay, so what this now tells us is that proving lower bounds for depth 3 circuits with respect to polynomials in VNP would actually separate VP from VNP. And maybe that's the goal for algebraic complexity, right? So, yeah. So already at depth 3, the question is interesting. If you are able to get the right kind of bounds, you will solve a major open problem, right? So these are the reasons why one would care about this. Okay, so then now that this question is important, what was known before this, right? So, of course, if we just take a sneak peek into the Boolean world, then really beautiful set of results came about in the late 80s that showed that constant depth Boolean circuits are quite weak. Very simple functions like the XOR function cannot be computed by them, even with exponential size. Okay, these were really celebrated results, beautiful results, and that led to many other interesting theories and so on. And the authors are listed, right? So that was very interesting. Now let's look at the algebraic world again. Depth 2 lower bounds in the algebraic world are trivial because if a polynomial has k monomials, then obviously if it is to be written as sum of monomials, you need at least k sums, k inputs into the sum gate. So even the very simple polynomial I showed you a couple of slides ago, which has 2 to the n monomials, will require 2 to the n sized depth 2 circuits. So depth 2 case is kind of very easy. But for depth 3 and above, not so much was known prior to this work. So for depth 3, for instance, almost cubic lower bounds were known. So just about n cubed by log square n. So this is a result by Kayal, Saha, and Sebastian again, Tavenas. And more recently, in 2020, for depth 4, a lower bound was proven. This was by Gupta, Saha, and Tamki. And this gave even lower than n cube, n to the 2.5 lower bound. And now if you look at depths higher than that, then in fact nothing better than superlinears known. So the kind of lower bounds that are known deteriorate pretty quickly with delta, and they are just anyway n to the 1 plus omega of 1 by delta, something.
Nutan, just a question out of curiosity and also to see if we're audible, which we seem to be. So one important thing of these lower bounds is that you want to lower bound circuits for building syntactically exactly these polynomials, right? Or does anything matter if I just say I want any polynomial that computes like I don't know, a Boolean function? Does the question make sense? Like, are the results robust in this way?
So you mean that I want to just compute any polynomial which has Boolean coefficients and then
which when evaluated on the Boolean hypercube?
Oh, yeah, that's a very good question. So that question makes perfect sense. So I think if I understand it right, correct me if I'm wrong. You're asking whether we can prove functional lower bounds. And
yeah, I think so, yes.
Yeah, so one of our results, which is for set multilinear polynomials, it holds over all fields. So in particular, it is functional. But some other results we have are over characteristic 0. So they stop being functional. And if we are able to prove them functionally, I think it will have implications to algebraic proofs as well. So it is an interesting question. It's one of the questions I list at the end as well. So we don't know whether we can make these functional. It would be a very interesting question. I tried to think about it. There doesn't seem to be an easy way.
Okay, thanks.
Yeah.
Similar, do you know if you had what the characteristics are for these lower bounds to hold?
Yeah, so I think in these, I think for these, the characteristic has to be large. Over here, I think it just works. Overall characteristics. Yeah, thanks. Yeah.
Also, previously you had the degree also being part of it.
Yeah.
Do these constructions have a large degree or?
Yeah, very good question again. So the candidate polynomials here, with respect to which these are proven, firstly, they are in V and P. So they are kind of the right place in some sense. The bounds are not tight enough. The degrees of all of them are controllable as a parameter. And usually they set it to all the way up to n in their low bounds. But it is a parameter one could play around with. I don't think it sort of helps to play around with it to push it any further, from what I understand. Yeah. Right. Okay. Any other questions? Okay, so this is the status quo before the result. And because this is a MIAO talk, I think there should be a cat. And the first so what we prove is a first superpolynomial low bound for constant depth algebraic circuit. So that's the result. Just to be formal, it says for parameters n, d, and delta, and d small, and characteristic 0, there is an explicit polynomial of degree d such that any algebraic circuit of depth delta computing it must have reasonably large size. So let's just try to understand this thing written in red here. It's n to the d to some inversely growing function of delta. And it would have been nice if this function was like 1 by delta, because that's sort of what we expect it to be, for reasons I will not go into right now, but that would be the right bound actually. But we don't quite get that. We get something like n to the d to the 1 by inverse exponential, so 1 by 2 to the delta or thereabouts. Okay, so that's what it is. Yeah, that's the low bound. Also, let me make the polynomial completely explicit. We do this for a very well-studied polynomial. So we show that this particular polynomial, which is called the iterated matrix multiplication polynomial, the lower bound holds. So what is this polynomial? We all know matrix multiplication. There are two matrices, you multiply them and you get some values. Now we have D matrices and you multiply them out. In this case, like we are used to in matrix multiplication, the entries of the matrix in matrix multiplication are values, field elements. Here they are variables because we are in the algebraic world. So when we multiply these matrices out, you get a final matrix, say A. Each entry of this matrix is a polynomial. And now, for the sake of concreteness, let's just say 1, 1th entry of this is my intended polynomial. So that's what it is.
And which field is that?
Say that again.
Like which field are you?
Which field? So currently this polynomial just has 0, 1 coefficients. So you could consider it everywhere. But our lower bound only works over fields of large characteristics. So the circuits are computing things over large characteristics. The final polynomial being computed is this polynomial, which has just 0, 1 coefficients.
I don't understand what the xi's are.
Yeah.
Xi's are sets of variables?
Yeah, good question. So this is slightly, I'm overloading xi. Xi is a name of a matrix, but xi, I also take it to mean the variables inside that matrix. Now, what are the variables inside every matrix? So let's look at matrix, say, x2. Then the variables inside that, I will think of them as, say, x with superscript 2. And then I, jth entry is, say, subscripts ij.
These are small x's.
Let me call them small, yes. So if there was just one matrix, then I, jth entry would have been xij. Now there are D matrices, so let's name them with some superscripts 1 to D. And now so every matrix is over a fresh set of variables.
So there are dn squared variables.
Exactly. There are dn square many variables overall, and D matrices, yeah.
And they're square free.
They are square free. They are very interesting polynomials actually. Firstly, every monomial is easy to understand because actually they can also be thought of as graph reachability, because every matrix can be thought of as an adjacency matrix for a bipartite graph with n vertices on each side. And from variable I to variable j, you have a variable xij. So now if I just start from, say, 1, 1th entry in the first layer and go to 1, 1th entry in the final layer, all the monomials I get along the way is this polynomial. Yeah, just sum of all those monomials is this polynomial. Whereas the monomial is computed by multiplying the edges that you encounter along this path, along all these paths. Yeah, so it's a very easy to understand polynomial. It comes up quite naturally because we care about reachability in the Boolean world and so on. Also, it is like Tho was saying, every monomial has at most one occurrence of any variable. In fact, every monomial can be viewed through these D sets, x1 to xd, and exactly one variable per set occurs. So it's all those things. It's this very special.
The walk polynomial for the D-partite directed graph.
Exactly.
Oh, now I like it.
Now you like it, right? So yeah, exactly. Right. So in terms of IMM, then the result is simply this. Any depth delta circuit computing this polynomial requires size n to the d to the inverse exponential in delta. We get something interesting at depth 3 actually. So at depth 3, we get the type bound because I already told you that any polynomial at depth 3 can be computed in size n to the order square root d. So we are also able to say that this is the best you can do at that depth. Yeah. So that's the result. That's the main result. So let's now check back. Did we prove something extraordinary? So
and sorry, this step 3 bound is tight. I mean, there's a matching upper bound.
Yes, because of the top line on the slide, this slide also. We know that any polynomial in VP and
oh, yes, of course.
Yeah.
Sorry, yes, sorry.
Machinery, but there's no easy way of seeing that this thing can be computed better than n to the d.
At depth 4, it's very easy to see. Just do your divide and conquer. Because split the layers into square root d, square root d, square root d, and just brute force. Yeah. So at depth 4, it's trivial to see that it's n to the square root d by divide and conquer. I won't say trivial. Let me take that back. It is easy to see. If we think about it, it's easy to see that it is n to the square root d. At depth 3, I don't know of any better way of showing this. Maybe there is some other way. I don't know that. For IMM, maybe there is a better way to do this, but I don't know any other way. Yeah. So coming back to this, what we would have liked is a polynomial f in VNP with n to the little omega square root d lower bound. So we miss the target by 2. Firstly, we only get omega square root d instead of little omega square root d. So, well, and then the polynomial we have is in VP. So obviously it's not going to be able to separate VP from VNP. Our target polynomial itself is quite easy. Okay, but it is believable that you can make this IMM polynomial somewhat harder and come up with a version that is in VNP or VNP hard, and now correspondingly push the lower bound to n to the omega square root d as well. So it's believable. Maybe it's like a step towards that. Who knows? But yeah.
In depth 2, I mean, is it also typed?
Depth 2, well, it's just sum of monomials. So,
So how many monomials?
n to the d.
Oh, just like.
Yeah. And there we know n to the d lower bound and upper bound. So that question for depth 2 is kind of just not interesting. Yeah. All right. So that's where we are. So here is one application. So what I just told you is the main result. So that's clear. And now what I'm going to try to tell you is one application of this result, which is to a problem that people in algebraic complexity care about. And a lot of you would have definitely seen it in many other places as well. This is called the polynomial identity question. You're given a polynomial, but not exactly given. You just get to ask questions about evaluations of this polynomial at different points. These are the kind of, so it's a query model where you ask, what is the value of this polynomial at this point? What is the value of this polynomial at that point, etc. And now at the end of these question answers, you have to tell whether the polynomial is identically 0 or not. You could also maybe have two polynomials, P and Q, and you could ask whether the two polynomials are identical, equal to each other or not, and stuff like that, which is the same as PID. Of course, a very simple randomized algorithm is known for this. Just ask the value of the polynomial at a random point, and we know that if the polynomial is indeed identically 0, then it will always output 0 with probability 1, and if it is not 0, then there's a large likelihood that the point at which you query the polynomial is going to output a non-zero value. Okay, so randomized algorithms are known. There's a big open question about, can we de-randomize these algorithms? And in general, there's a nice hardness versus randomness connection that has been established by Cabanets and Impagliazzo, which says that, which in particular, it says many things, but in particular, it also says that if VP is not equal to VNP, then the polynomial identity question for circuits has deterministic sub-exponential time algorithms. Okay, so deterministic sub-exponential time is a bit loaded, but just think of it as it can be de-randomized with non-trivial gains, because exponential time, you can always de-randomize anything. It's saying if you spend even sub-exponential time, you can still de-randomize it, as long as you're able to show that VP is not equal to VNP. In particular, if you're able to show there's a polynomial that cannot be computed by small size circuits, then in fact, you can de-randomize this randomized algorithm. There's a version of this result which is known for constant depths as well. So if you're able to show that there is a polynomial that's provably not computable by small depth circuits, then in fact, polynomial identity question for small depth circuit becomes de-randomized. So de-randomization works out. So basically the hardness versus randomness paradigm is like this, that if you are able to show hardness with respect to a certain model of computation, then a certain algorithmic task about that model of computation becomes easy. So the first result written on the first box in the slide says that if you are able to show that somehow polynomial-sized circuits, that's VP, are weak, there's some function that they cannot compute, then everything that is computable by them, the PIT for that can be de-randomized. So similarly, we can scale down the result. That this is a result by Chow, Kumar, and Solomon. And this gives us the exact recipe we need to sort of de-randomize PIT for constant depth circuits. Because look at the premise in the second box. It says, if you can give a polynomial that is hard to compute for constant depth circuits. Now we are able to give a polynomial that is hard to compute for constant depth circuits. So putting that R hardness result along with this conditional result, we get de-randomized PIT for constant depth circuits. So that's the result. Given black box access to a constant depth polynomial size circuit computing a polynomial P O x1 xn over characteristic 0, there is a deterministic algorithm. So for any polynomial that is computable by this model of computation, which is constant depth, we get sub-exponential time running time. So I said a lot of things about PIT. Maybe it was a lot. But just to summarize in one line, polynomial identity question for constant depth circuit is now solvable in deterministic sub-exponential time. What was known prior to this? So the best result for depth 3 till date is this result by Saxena and Shashadri from 2012. It says that the PIT for depth 3 circuits can be solved in time n to the k. Where what's k? K is the number of wires feeding into the top plus gate. Okay, so actually this is a very well studied question in algebraic complexity, trying to do de-randomization of PIT for constant depth circuits. And for different restrictions on the circuits, lots of results are known. I'm just telling you one of them. This is considered to be the best for depth 3. So you can see that if the top gate has span in 2, 3 or some constant, then they get a polynomial time running time algorithm for PIT of such circuits. We, in no paradigm from our result, will get a polynomial running time. It's always sub-exponential. On the other hand, if the k value there, that is the number of gates feeding into the top plus gate, is somehow a function of n, then say it's n, for instance, then their running time becomes pretty bad, which is order n to the n. So then sub-exponential time starts to look better. Right. So just to say that these results came about because there was already a recipe ready for this, and our lower bound just fit right into that. So that's one of the results we have.
So that was Cabanets and Pagliazzo and...
Oh yeah, sorry, I should tell the name. So Cabanets and Pagliazzo were the ones who kind of started this hardness versus randomness in the Boolean setting. The result has been adapted by, again, multiple in multiple ways in different fields. But in algebraic complexity, in 2009, Dvir, Shpilka, and Yehudev used this to prove something about constant depth circuits. But in their result, the degree was not small. Later, in 2018, Chow, Kumar, and Solomon did this for constant depth with small degree, which kind of exactly what we needed somehow, and it existed in the literature. So that's the line of work that I'm aware of in this this history. All right. There's another refinement of the lower bound result we have. I told you that there's an IMM. That's a polynomial that is in VP, and any constant depth circuit cannot compute it unless it spends a lot of space, a lot of size. You can refine it by saying there is a polynomial at depth gamma, which can be computed by size as circuits, but any gamma minus 1 already requires size more than S. So, and this is true for all gamma. So that's kind of the hierarchy theorem, depth hierarchy theorem. So that summarizes all the results. So how am I doing on time?
You're doing fine. 18 minutes left.
Good. Okay.
Plenty of time.
Schedule proof, exactly. Okay, so I am going to mainly talk about this result now because, as I told you, the polynomial identity testing as well as the hierarchy result kind of are whatever overflow of these things, this result. So let me go into proof outline. Maybe I can pause up for if anybody has some questions. But if not, let me continue. Feel free to unmute yourself for the online audience. Right. So now, the main proof idea in trying to prove this is that of escalation. Escalation, I'm just giving it a name. What I'm trying to say essentially is if you prove lower bounds for some weak model of computation, then there is some other machinery we can append it with so that it implies lower bounds for the model we want, which is general circuits. Okay. And because I'm going to talk about some weaker models of computation, let me quickly introduce those. So we are going to talk, I mean, these are all terms I'm sure all of you already know. Homogeneous polynomials are polynomials where every monomial has the same degree. Multilinear polynomials are, maybe fewer people know about multilinear polynomials. Multilinear polynomials are polynomials where in every monomial, every variable occurs at most once. There's also something that we will use, which is called set multilinear polynomials. Well, set multilinear polynomials are polynomials where you already have like a set structure, x1, x2, xd. And every monomial in your polynomial uses exactly one variable from this set. So IMM is one such example, like Thor already pointed out. Yeah, IMM is a set multilinear polynomial. I did not give it a name, but well, now we call it set multilinear polynomial.
Is it important for you that it's exactly one variable per set? I mean, because the multilinear just says at most, right?
Yeah, it is important. So the model is kind of, each monomial is homogeneous and it is over every element of the set. Yeah, it is important. Okay. Yeah.
Thanks.
Yeah. So for the types of polynomials we saw, there are corresponding models of computation. This part is not at all surprising. So a homogeneous circuit is a circuit where every gate computes a homogeneous polynomial. Multilinear circuit is a circuit where every gate computes a multilinear polynomial. And a set multilinear circuit is a circuit where every gate computes a set multilinear polynomial over the set of variables it is viewing at this point. Yeah. And then eventually it will view all sets. Yeah, so this is all that. This is the only jargon kind of thing that we use. Okay, so here is an escalation idea. Escalation idea is not new, neither in algebraic complexity nor in complexity theory in general. I think Jakob and others are more well positioned to tell you more about such results in other areas, but they are there everywhere. Here is one instance of such a result. What does it say? It says that if you give me any arbitrary formula of size S computing a polynomial P, then I can turn it into this very structured set multilinear formula. Okay, so I can forcibly make it set multilinear as long as it's computing a set multilinear polynomial. If it's not computing a set multilinear polynomial, there's no hope. But if it's computing a set multilinear polynomial, then I can actually structurally change the circuit a little bit so that now the circuit becomes set multilinear as well. Every gate follows this rule of being set multilinear. And in doing that, you do incur some blow up, and it's not important what that blow up function is. You can take a look at it. I'm not going to read it out, but let's instantiate this function for a specific d. Let's say d is like some small function of log n. Okay, and say the formula size we start out with for polynomial p is polynomial, poly in n. So if we start with polynomial size formulas for a polynomial p, then that result of RAS says that you can actually turn it into a set multilinear formula without basically no blow up at all, as long as d is small. So that's quite nice, because this escalation, now from here, if you look at the contrapositive, escalation follows. It says that now if you prove superlinear lower bounds for just set multilinear polynomials, which are set multilinear circuits, which are restrictive, then they imply superpolynomial lower bounds for general. So the previous slide and the next slide are just contrapositives.
You also switch formula to circuit at some sneaky times here. Is there something under the rug?
Yes, actually, the thing is that RAS's result only holds for formulas, not for circuits. Yeah.
But then on the next slide, you suddenly talk about circuits.
Am I?
I feel cheated. No, maybe just your words said.
I should be saying formula. I'm sorry. Yeah. I think the slides are fine, but I misspoke. Sorry about that.
This doesn't say anything about height. Depth, sorry.
Very good question, and I'm happy. Yes. So the thing is that actually this does not preserve the depth. Even if you start with depth 3 formulas for polynomial p, the depth is going to get blown up. This is how his construction works, essentially. So we don't have any control over the depth. So RAS's result is ripe for escalation. If in the past somebody had proved strong lower bounds for set multilinear formulas, maybe that would imply lower bounds for general formulas. But one caveat already is that this is not depth preserving. So that's a problem. There are a couple of other, not so caveats, but sort of shortcomings of the previous results. So a lot of work has happened in this set multilinear world, though not too many people outside of algebraic complexity would have heard about set multilinearity. There are lots of papers. I'm not even mentioning all of them here, but these are like the hallmark kind of papers that proved set multilinear constant depth formula lower bounds over the last several years. But all the lower bounds known were of the following form. There was lower bound that was some exponentially fast growing function of f of d and poly in n. Now,
I'm still curious. Nissan Wigderson?
Oh yeah, of course. I will say Nissan Wigderson, RAS and Yehudeov. Yeah, sorry. Yeah, but for escalation to work from the previous slide, we needed results which had d in the exponent of n somehow. The function, the kind of lower bound we needed were of the quality that d was sort of in the exponent. So just from the literature of fixed parameter tractability, we just call these sort of lower bounds non-FPT because they have d growing as a function that is in the exponent of n. And what we would like are such lower bounds, because these are the kind of things that seem to escalate. Okay, so a couple of things. We want an escalation result and then a lower bound for set multilinear formulas. That's not the only way to prove this, I'm sure, but this is how we prove it. So to state the set multilinear formula lower bound, our formula lower bound says that for all constant depths delta, we actually get non-FPT lower bounds for set multilinear formulas. So the quality of the lower bound you can observe is exactly like the one I have mentioned in the general formula or general circuit lower bounds as well. So just to read out what is on the slide, for small d and any constant delta, we show that set multilinear circuits computing IMM of depth delta must have size n to the d to the inverse exponential in delta. That's the lower bound we have. We have something more specific at depth 5. At depth 5, we get n to the omega square root d, and I'll say a little bit about it later. Let's ignore these 2 points for now.
Sorry, the lower bound in the previous slide, those are for Boolean circuits or algebraic circuits?
Which one?
Previous slide.
These are all algebraic. Yeah, these are all algebraic. Yeah. Boolean constant depth is sort of a resolved problem in some sense now. Right? So over binary, over ands and or spaces, even over XOR and finite fields, constant depth lower bounds are known for a long time by Rasbro and Smolensky. Yeah. All right. So what I just told you is that we have a set multilinear form, set multilinear lower bound, which is in quality matching the lower bound we are hoping to prove for general circuits. Now I'll tell you a little bit about the escalation we have. Okay. The escalation result we have, as I said, first should do efficient simulations, and then in contrapositive it will give us escalation. So for efficient simulation, take a general circuit of size S and depth gamma, computing the polynomial P. We show that over characteristic 0, we can convert it into another circuit which is homogeneous. So every gate is now homogeneous. The depth becomes almost twice 2 gamma minus 1, and the size takes a hit of a certain function that is multiplicatively hitting poly S. And the function is 2 to the omega square root d. It's some exponentially growing function of d, but the important thing is it just multiplies poly S. So this is one result we have. And then from homogeneous, we show that you can go to set multilinear. In this step, you don't even blow up the depth at all. The depth remains exactly the same. This result also works over all characteristics. So, it just works. And the size blow up now is like d to the order d. Okay. Again, the quality of that blow up is kind of what we like, because immediately in contrapositive, it starts to say that if you give me superpolynomial lower bounds for set multilinear circuits or non-FPT lower bounds for set multilinear circuits of depth 2 gamma minus 1, they imply non-FPT lower bounds for homogeneous circuits of depth 2 gamma minus 1. And in turn, they imply superpolynomial lower bounds for general circuits of depth gamma. Okay.
So
yeah.
The polynomial, is that even when you go from general circuit to a homogeneous circuit, is that a set multilinear polynomial, or
yes.
is it a...
Yes.
Okay.
Yeah.
So it's not for general homogeneous.
Okay, sorry. So the conversion works even if it's just homogeneous. Okay. Yeah, you're right. Yeah. So for the first conversion to work, we don't use anything about set multilinearity. Thanks. Yeah. So what this now says is that if you prove lower bounds for set multilinear circuits, they give lower bounds for general circuits and also PIT and so on. So that's the escalation. So now a one slide summary of the result basically is at the top, what I've written is the set multilinear formula lower bound, circuit lower bound. And below it, I've talked about the escalation. So really, this is all I wanted to say, but I will close with a few open questions, which may be of interest to some people in the audience. So, of course, if there are any questions, please feel free to ask. All right, so now one open question we would like to resolve really is to improve the quality of the lower bound. There's no reason for this lower bound technique to stop at n to the d to the some inverse exponential in delta. Really, for reasons that I haven't mentioned in this talk, the correct upper bound is sort of n to the d to the 1 by delta, at least for IMM, by divide and conquer. And therefore, we would like to prove a lower bound of this sort, at least for IMM. It makes sense to want to prove such a lower bound. We don't know how to do that. Another interesting question is, there was this annoying characteristic 0 in one of the steps of the escalation, and it would be interesting to get rid of that. We have a few ideas, but none of them seem to work.
Can you say anything about why characteristic 0 would come in the first place?
Yeah, so vaguely speaking, we are using something called as Nutan identities. Nutan identities are transformations that take polynomials, symmetric polynomials, and write them on another basis, over power symmetric basis. So, and in doing that, we do division by large constants. So we need to divide to get one polynomial from another set of polynomials. We need to divide by a constant. And let me also plug in a thing for the longer part. So in the longer part, I'll explain. But in any case.
Is that also where you need a field?
Yes. Yeah, no, that is the only place. That is the only place where we need characteristic 0. And if we can get rid of that, then the result will hold over all characters, which will be much more satisfying. Another set of questions which are sort of more interesting for people who are kind of into algebraic complexity, I think, but maybe otherwise too. So PIT, polynomial identity testing results sort of came out because of this hardness versus randomness machinery which was there, plus our result. So it's known to happen that polynomial identity testing becomes easy if lower bound is known for a model of computation. Similarly, some other questions like the reconstruction question, which I will not define right now, but it's also another question that people in algebraic complexity like to consider. And it is known that there are models where lower bounds were proved first and then reconstruction followed for those models. So it's possible that there's something there. This also another question which Jakob, I think, was kind of asking about. So if our result, which is for general circuits, becomes functional, in that we think of it as a lower bound over evaluations rather than polynomials, vaguely speaking. If the lower bound holds even in that setting, then it is possible that algebraic proof complexity results will follow from this. So that's also an interesting avenue to explore. And then, of course, again, very technical questions. I mean, not very, but kind of technical question of more interest to people in algebraic complexity, I suppose, is to just understand these lower bound techniques. Now, is this a new technique that we have, or is it like something that we just applied to something else? So there's maybe a little bit more we need to understand about how this lower bound kind of came about. So yeah, so we would like to understand that as well. So that's it. Thank you for your attention.
Thank you very much, Nutan. What a result, a very inspiring talk. What happens now is that there's a brief break. There's coffee and cake. And for those who want this session, I think we'll continue in this room and online.
Yeah.
And I think the master of ceremonies in this room may be the Swedish ones. Correct? That would mean that at some time you need to clap your hands to get everybody into the room again, and somebody needs to make that the online audience, to which we extend our warmest wishes as well, feels plugged in. I just know that I need to be somewhere else.
Yeah,
so.
thanks, Dor. And at what time do we start? Do you also announce that?
Yeah, so joining in from the virtual world, I guess the question is, you physical beings, how long you want to have your cake munching? Usually we would do somewhere between 5 and 10 minutes of break. What do you think? Should we reconvene like at 10 minutes past, or even faster?
Back at 5.
What's the time now?
It's
back at 15:10 CEST.
Yes.
Okay. Good. Thank you so much. We'll be back in 9 minutes. So we're back after the break. Some of us got cake. Others, virtual participants, did not, but we'll try to soldier on for the second half anyway, when Nutan promised to tell us about some of the details. She left some teasers about during the first half of the talk. So Nutan, without further ado, over to you.
Yes, thank you so much. Thanks for staying back for whoever is here. So like I told you in the previous part of the talk, we proved the general circuit low bound result by combining two ideas. One is the escalation idea, and the other is set multilinear circuit low bound. So my plan for this part of the talk is to kind of give you the sketch of both of them. And I will try to focus on the case of gamma equal to 3. That is, I'll try to prove sigma pi sigma circuit lower bounds. This is already new. Superpolynomial lower bound for depth 3 general circuits was not known prior to this, as I told you. The best lower bound there was almost cubic. So this is kind of the result at the smallest depth level, which was not known. I'll try to present this. And because of this escalation, what that means is I need to prove a lower bound for set multilinear formulas at depth 5. So that's what I will do. I will try to show you how to go from, how to work out these escalation results starting from depth 3 general circuits. Then I'll simulate that depth 3 general circuit by homogeneous circuit of depth 5. And then that homogeneous circuit of depth 5 by set multilinear circuit of depth 5. And then, so that will do the escalation for this depth. And then I'll try to prove the lower bound for depth 5 set multilinear. So that's the plan. I'll try to get through with this.
Just to ask a question right off the bat to increase the interactivity also. So when we talk about escalation or amplification in proof complexity, one thing that often happens is that you like take a problem and then you prove some kind of weak lower bound for it, and then you massage the problem. Like say you have some, formula, and then you replace every variable by an XOR of two fresh variables or something. But here you're actually working on the same problem the whole time. Or has this like substitution or lifting or something, anything in that direction done in arithmetic circuit complexity, or not so much?
Not so much that I'm aware of, but maybe a little bit. For example, when one tries to prove relationships between non-commutative and set multilinear circuits, then sometimes a substitution idea sort of works, because non-commutative circuits and set multilinear circuits can be thought of as almost similar. If you think of these sets coming in a specific order and then variables multiplying in that very order. So, but I wouldn't call it the same at all. I mean, it's not like what happens in lifting or something like this. So I don't know of that kind of thing working here. But it's also possible that I don't know all of the picture. So.
Okay, thanks.
Okay. All right. So so let's try to do these results. Wow, why is it rendering like this? Okay, I didn't plan for that to happen. Yeah, this is what should have happened. Yeah, good. So we want to do this in 2 steps. First step that I'll try to work out here is to go from homogeneous formulas to set multilinear formulas. Okay, because this is characteristic independent and it's very, very easy to describe. So let me do that first. Okay, so just to read off the slides. Let's say we have a circuit of size S, which is homogeneous, computing this polynomial P. How can we make that circuit set multilinear? We know that the polynomial itself, the target polynomial, is set multilinear. How can we make every operation inside the circuit set multilinear? And the simple idea is to blow up the circuit a little bit. By that I mean, let's take a gate G in the original circuit. Now this has degree delta. Now it's a homogeneous circuit, so what I know is every gate computes a polynomial of a certain fixed degree. Every monomial inside that has the same degree. So let's say for this gate G, the degree is delta. Its children are G1 to Gr. Say. Now, what I'll do in my target circuit, which is going to become a set multilinear circuit, I promise, is that I'm going to put the copy of G along with T many copies of sets. So there are going to be T copies of G, G comma S1, G comma S2, G comma ST. Where what are these sets? These are all subsets of size delta coming from the universe of size D. This makes sense because what I'm trying to say here is that I want to build a polynomial which is set multilinear, which means I want to club together all the monomials coming and feeding into G into sets which only rely on a specific subset. So what I just do is by brute force, just make so many copies of it and try to collect together monomials into G comma S1 for the part of G which only relies on S1 and so on. Okay. And there is a very simple way to do this inductively. For example, if G is a plus gate, right? Then what would you do? Well, if G is a plus gate, and inductively I have similar copies of gates for its children, then for the corresponding gate G comma S, I'll build a plus gate in the target circuit with G1 comma S, G2 comma S, GR comma S. The same set of, because plus gate cannot introduce new variables into the set. So if the target polynomial that I'm trying to compute is with respect to the set S for the gate G, then its children also must be picking up polynomials only from the corresponding gates. So if G is plus, it's simple. If G is a multiplication gate, then what is going to happen is, suppose G comma S is the gate I want to finally, is the polynomial I want to compute. So I want to put together all the monomials which rely on the set of variables coming from S. Then I need to figure out all possible ways of collecting monomials from the children of G, which will contribute to S eventually. So basically, if it had only two children, then if G had only two children, then say G1 and G2, then it's easy to visualize. I'll just take G1 with a set S prime and G2 with a set S minus S prime, because these together, when they multiply, their variables will result into the set S, right? So then what I do is so let me write it slightly more clearly. So I multiply these, but this is not enough. I need to do this for every subset S prime of S. So my resultant circuit is going to be like this. G1 comma S double prime, G2 comma S minus S double prime. But in fact, I should write it very, very, very clearly for two sets. It's basically sum over all subsets S prime of S such that, and for each such set, I add G1 comma S times G1 comma S prime times G2 comma S minus S prime. This is the whole computation, because these are the only things that can, if G had two children, these are the only things that can feed into G eventually. And if G had the maximum number of children G can have is delta. So you have, currently I worked this out for two sets, and you will get a blow up of D square in number of gates because of this. Because you'll have, this is a set of size delta, and I'm looking at all possible subsets of delta, so something like 2 to the delta. But in general, you might get a blow up of something like D to the D. That's what is the overall blow up here. So if this is not clear, please ask me questions. I'm doing something brute force, more or less. Okay. So what that did was basically you put together target gates that you want to eventually compute polynomials for. And now for every target gate, see what contributions will be feasible from its children, put them together. Note that while doing multiplication gate, I added this plus and then a multiply. So it may seem like the depth has blown up by 2 because for every multiplication layer, I add a plus and a multiply layer. But then the plus layer added here and the plus layer from layer above can just be collapsed. So there's no blow up in depth, and the blow up in size is, you can imagine, is d to the order d. Yeah, I'm not going to work out the last bit of the constants, but it's probably clear. Okay. What we used non-trivially here was the circuit we started out with was homogeneous. So as a result, we could assume that multiplication gate had a certain fixed arity. It can't be arbitrary. Okay, so that's step number 1. That was quite direct. For step number 2, what do we need to do? We need to start with a general formula of depth 3 and come up with a homogeneous formula of whatever depth. Let's see what depth comes out. In order to do that, let's look at what depth 3 general formula looks like. It's a sum of products of linear forms. Well, they are affine forms. And I can make the constant 1 by scaling. I'm already assuming large fields here when I do division, but anyway, the result holds over a large field. So let's just assume that. And now I'll try to tell you how I can compute a degree d factor of any one of these terms. So let's look at one such term. A specific term could have any number of product gates feeding into it because, you know, it's not a homogeneous circuit. So cancellations can happen and finally the degree could become d, but a product gate could arbitrarily have degree some, say, capital D. We have no control over what this capital D is except the size of the circuit. It's upper bounded by the size of the circuit. So now how do we evaluate one such gate? Note that if I'm interested in degree I component of this term, I'm essentially interested in a symmetric polynomial over these LIs. For instance, if it was x1 plus 1 times x2 plus 1, and I needed a degree 2 component of this, degree 2 homogeneous component of this, then it's just x1, x2, which is the symmetric polynomial of degree 2 over 2 variables. And this is true for general D. So I'm interested in computing symmetric polynomials of degree I over D variables. And there's a result which is known as Nutan identities. Which says that, in fact, this can be expressed as a sum over power symmetric polynomials. What are power symmetric polynomials? So symmetric polynomials, I hope we all know what they are. Power symmetric polynomial of degree D, power symmetric polynomial of degree I over variables x1 to xn is simply sum over I going from 1, let's say j going from 1 to I, xj to the I. So you just add every variable to the power I, that's the degree I power symmetric polynomial. What's known is that symmetric polynomial, which is one basis in which you can write a polynomial, can be expressed over another basis, which is the power symmetric basis. These are called Nutan identities. And you can write them as degree 1 power symmetric polynomials, degree 2 power symmetric polynomials, power symmetric polynomial of degree 2, m2 times, etc., up to degree I power symmetric polynomial up to the power mi, where the property these mi's have is that j times mj, j going from 1 to I, sums up to I. So, you know, so a very simple example, to compute x1, x2 using power symmetric, how will I do it? I'll just say it is x1 plus x2 the whole square minus x1 square minus x2 square. Yeah, so these are all power symmetric polynomials, note, by 2. Yeah, and kind of this result generalizes for all capital D. This is what I have written here vaguely.
Is there any reason to use this basis and not one of the other bases for?
Good question. Good question. So there are a lot of bases known for symmetric polynomials, like homogeneous basis, or you have the sure polynomial basis, and so on. The thing is, all those polynomials are very hard to compute. What's amazing about power symmetric polynomials are they are so easy to compute. So Newton identities, therefore, in algebraic complexity are very useful because symmetric polynomials, which are generally expensive, are computed quite easily using these power symmetric. In fact, that's of interest to us immediately. This question is like Jona's question, you know, right on time. So the thing is that why this is useful is because now I can bound how much I'm spending in order to compute such a thing. So I wanted to compute this. This kind of is an expensive operation, but instead I'll compute this. And computing this, well, I won't work it out, but it has a blow up of only something that depends on D. This capital D, which is the number of linear forms that I'm working with, doesn't come into the picture. This is the interesting thing.
And from your small example, we could already see that here, this wouldn't work in characteristic 2, for instance.
Yes, exactly. Exactly. Another very important point. So in Newton identities, what happens is when we go from one basis to the other, there's this constant that scaling factor that comes about. And typically it is something like, I think the character on characteristic little d or larger than maybe 2d or something, everything will work out. But there is a division by d. In fact, there is, I think, 1 by d factorial or something like that. So is that right, Radu? I'm kind of unsure, but I think.
I'm also not sure.
Yeah, I think it's like d factorial. From what I remember.
Yes.
Yeah, yes. So Radu confirms.
Would you like to point out this connection to the determinant? Because
yeah,
these Newton identities come historically from the determinant, or a particular way of relating the determinant to traces of matrix powers.
Yeah. So, I mean, I'm not the right person to talk about this. Radu is commenting, so I'll just relay the comment here. That is that basically this has close connection to computation of determinants as well. And if you look at traces of the matrix, then there's a way to represent, of course, there's a way to define determinant in terms of the trace. And that again relates back to this sort of conversion. Even there, I think there is a dependence on the fields. And so, yeah, there are interesting questions about how we can get rid of the dependence on the field. Yeah.
So these identities essentially come like historically from this fact that the determinant of the matrix is the product of the eigenvalues, assuming that we're going to algebraically close field. And like the trace of the matrix is the sum of the eigenvalues. And if you then take the trace of a square, you get the sum of the eigenvalues squared and such. Yeah. So if you compute a to the t and the trace of that for sufficient many t, then you get these evaluations of power sum polynomials of the eigenvalues. And the Newton identities allow you to recover the product of the eigenvalues from these power sum, from this power sum data, essentially. Yeah. And like this is the formula how you can get back. And this is where this is coming from in like the 19th century.
Yeah. Yeah. I don't know whether the live audience was able to hear this.
Oh, yeah.
I think we can hear reasonably well, or at least, yeah.
No, I wouldn't agree with that, but I think if you could hear that, then I don't have to relay it. Okay. So this kind of does the two steps for depth, I did not argue why the depth is only 5. And that's actually quite clear, because you have this sum that will stay as is, I guess. Each product is going to be written as this big sum of powers of and their powers. So it kind of becomes sum of powers. I represent powers by this wedge here. Then again, like a sum powers. Okay, so because these are the powers that are outside, I'm not going to write everything here, but so, okay, let me be a bit more clear. Sorry for the last 2 mumbled sentences. One more time. You have this 1 plus gate. Then each term is being written as some sum of certain products. Now this sum and this sum I'm going to just merge. Okay, so forget about this sum now. Now we have like a product. So there's a big sum, then there's a product. The product is of certain powers. And if the base power polynomials were over a set of variables instead of over linear forms, then we would be done. This would be it, because there were some powers here and then sum of powers here. But then now there are linear forms feeding into this. Okay, so you can work it out that the depth kind of becomes 5 here after enough merging of consecutive plus layers and multiply layers as required. And the size blow up is 2 to the square root d, simply because the number of ways of coming up with m's, m1, m2, md, such that j times mj summation j going from 1 to d equals d. It's like some partition problem. And this we can upper bound by some AMGM type arguments is 2 to the order square root d. Not important, but it's doable. So, okay.
So for larger depth, then you do the same thing with just a more complicated expression instead of a linear form, or like.
No. So for the larger depth, we need to use another trick.
Okay.
Yeah, it's a slightly different proof. So what we need is a generalization of Newton identities. And how? So in Newton identities, what we were able to do was every term was expressed as product of linear form. So each of this had degree 1. But at an intermediate point in the circuit, when we are trying to do this, you can imagine that at a product gate, you have things, affine forms feeding into it, but these are not simple degree 1 polynomials. They are like degree some polynomials. So this kind of becomes like you want to do weighted Newton identities. Where weighted, I mean that the inputs feeding into your product term each have different degree, say D1, D2, D3, etc. And now for such things, instead of degree 1, for such things, we need to come up with Newton identities. They were known. Weighted Newton identities. This is, we used a couple of different results. One is a proof by Limaye-Bink identity, or Bink-Limaye identity. And another proof is by this combinatorics paper by Bera and Mukherjee, which we stumbled upon. And there are 2 different proofs for higher depths. Both of them sort of give similar results. But basically, the key word here is weighted Newton identities, and they were known. So set multilinearization, this is the, again, 1 slide summary of what I just told you. And for homogenization, again, 1 slide summary of what I told you. So if the slides are useful for later. I should give the right credits here. So homogenization actually can be ascribed to Spilka and Wigderson at depth 3. This is not something that we discovered. It's just useful. This was known. Higher depths, I don't think it was known prior to this, so we were able to work it out. But at depth 3, it was known. This is, I think, 0, 1. if I'm not mistaken. Then it's also used in another paper for depth reduction in algebraic complexity. And it is also mentioned in Rubesh Yehudev's, one of Rubesh Yehudev's papers. Amir is here, so it's a bit odd to refer to him by the last name, but for the sake of consistency, let me do that. All right, so now all we need to do is the lower bound, set multilinear depth 5 lower bound, because escalation we already did at depth 3. All righty, just to emphasize this, I did not emphasize in the shorter version of the talk, but let me just emphasize it over here. At depth 5, basically we are going to get n to the square root d lower bound. So not just that d to the inverse exponential, we can actually pin it down to half, n to the d to the half. So that's the thing. And then at depth 5, of course, this is tight. So because you have the 4 circuits of this size. Yeah. Okay. So then let me just tell you what was easy to do before this and then what was the new thing. So
Nutan?
Yeah.
Hi.
Hi,
Can
Amit.
I ask a question?
Yes, please.
Do you need the set multilinear circuit to be homogeneous, or this is just a way to make it set multilinear?
No, we need homogeneity there, because to get the blow up of d to the d, the product gates must have Fanon bounded by d.
So you described a specific way to take a circuit and make it into set multilinear.
Yeah.
And the blow up is d to the d.
Yes.
Is it important that the thing you generated is also homogeneous or not? I don't know.
Okay, so the resulting circuit you are asking, the resulting circuit
Yes.
came up. I think if no, I don't know this. Yeah, I don't know.
The lower bound uses homogeneity as well.
I think as far as I can see, we use set multilinearity. Let me think about it for a minute. Yeah, we will. I think we'll need homogeneity actually.
Because so just making a circuit set multilinear is somewhat similar to computing a permanent version of the permanent.
Yeah.
And I think this type of computation was like, there are non-trivial ways to do this.
Yeah, I think you're right. I think we are using homogeneity as well.
Okay, thank you.
Yeah, yeah. Thanks for that question. Yeah, kind of made me think. Yeah, I think we are using it. Yeah. Any other questions? So now let me tell you how typical lower bounds work in algebraic complexity. This is sort of a recipe for any lower bound that we know, more or less. Of course, there are some other lower bounds which don't fit this recipe, but many lower bounds we know fit this recipe. The idea is to come up with a measure that maps polynomials to real numbers. And then the polynomial we want to show is hard. For that, we show that the measure is quite large. And for the model which we want to prove lower bound for, we show the measure is quite small. So now if the model alleges to compute this hard polynomial, then it better have some sort of a contradiction. And the contradiction is, if we assume that the size of the model was quite small, then the measure will be small with respect to the size. But then if it's computing this polynomial, it better be large. So the size better be at least as much as the hard polynomial's measure. Okay, so very vaguely speaking, this is how it works. And just a second. And now I'll show you the proof that was known for depth 3 set multilinear. We are going to prove depth 5 set multilinear lower bound, but for depth 3, really strong lower bounds were known by Nissan and Wigderson from 95. So let me just tell you that proof, and that uses this recipe. And our proof sort of uses a lot of components of their lower bound also. So it's useful to know this. Okay. So you have the base set of variables coming from the universe 1 to D. And suppose I partition them into 2 sets, and let me just call them positive sets and negative sets because it's easy to say positive, negative than P, N, and then getting confused. So, so they'll have a meaning in our positive, negative sense later, but really for this outline, we don't need them to be have any meaning other than letters P and N. So now let's consider a polynomial f, and for a polynomial f, I define the following very simple matrix. What I do is, for this partition of the variables, I list down along the rows all monomials which are on the set of variables coming from the positive sets. And along the columns, I list down monomials that can be obtained by taking variables coming from the negative sets. Okay. So for instance, D was 4 and odd numbered sets 1 and 3 went into positive set and even elements 2 and 4 went into the negative set. Then all variables that are labeled from sets 1, 3, all possible monomials that can arise from those 2 sets, they list the rows and columns correspondingly. And now for any row and a column, the entry M1, M2. So basically the upshot is the rows and columns are labeled by monomials. Yeah, monomials are resting on these sets P and N. And now for an entry M1, M2, we just put the coefficient of the monomial M1 times M2 at this entry. Okay, it will become a little more clear. We call this, yeah.
Just to make sure I understand.
Yeah.
So if is a set multilinear polynomial.
Set multilinear polynomial, yeah. Okay. Yeah. So currently I'm just defining all of this under set multilinearity assumption. Yeah, otherwise it may not make sense. Yeah, you're right. Okay, so just let's be concrete, okay? Let's just try to look at the matrix for the IMM polynomial, which we understand well. So IMM polynomial, if I just write it as sum of monomials, looks like the first line on the slide, yeah? You take some edge from the first layer, then follow it up with the same I1, I2, I3, etc. And now suppose my partition is all even layers go into the set N. So variables from the even layers go into set N. Variables from the odd layer go into set P. And let's say D is even. So just for the sake of clarity. So then what do we have? We have at the entry M1, M2, the coefficient corresponding to M1, M2. So for IMM, what will we have? The coefficient, that entry will be 1 if and only if the monomial M1 and monomial M2 break up nicely as a specific monomial inside IMM. So if indeed we have monomial labeling the row this one and the monomial that labels the column this one, then it will have to be that I1 is equal to J1, I2 is equal to J2, and so on for this entry to be 1, because those are the only monomials that are in IMM. All other monomials for other combinations of I1, J1 are not in IMM. Yeah, am I being clear here, or should I just explain a bit more? For the online audience, I don't know how to do this. Maybe I can do it here. Where am I? Yeah. So basically, these variables are going into odd sets, and say these variables are going into even sets. Then this entry, this complete matrix is just a 0-1 matrix, with a 1 appearing only when the monomial labeling the row and the monomial labeling the column gives a valid monomial inside IMM. All other places it will just be 0. And when will it give a valid monomial? Exactly when x1 I1 then stitches together with this variable, which then stitches together with this variable, which then stitches together with this variable, and so on. So for this particular case, everywhere else is going to be 0. So this is essentially an identity matrix for appropriate ordering of rows and columns. For exactly one entry, for every row, there's exactly one column where it's a 1, otherwise it's a 0. So it's full rank. This matrix is full rank. So what did we just do? I defined a measure. The measure was going to be for any polynomial, write its coefficient matrix as so. And now for a specific partition of variables, write its coefficient matrix and analyze its rank. For the IMM polynomial, if I consider the partition to be even and odd for positive and negative, then it gives full rank. Let's try to analyze a circuit of depth 3, which is set multilinear, under this partition or under any partition for that matter. Okay. Let's consider any arbitrary depth 3 circuit, which looks like this. It's a set multilinear circuit. It's Set multilinearity in specific also means this, that the linear forms at the leaves only depend on one set of variables. So if linear forms depend on only one set of variables, it's a rank 1 matrix, because it's just a linear combination of variables coming from exactly one set. So it's a rank 1 matrix. A rank measure we know is subadditive and submultiplicative. So we can also say that the rank of the product of these LIs is also at most 1. Yeah, it's just a rank, so a measure. And by subadditivity, we can say that the rank of this entire polynomial, which is depth 3, computable by depth 3 set multilinear formulas, is at most this summation, size of this summation, which is S. Okay, let's try to remember this as well. What I'm trying to say here is if any depth 3 circuit is analyzed through the lens of a rank measure, then if it is being computed by depth 3 size S circuit, then its rank is at most S. This is a general statement I'm trying to make. But now, if this depth 3 circuit, depth 3 set multilinear circuit, alleges to compute the IMM polynomial, then by that largeness and smallness argument, we'll have to have that the size is at least n to the square root d. Because, yeah. So this is the recipe I told you about. Come up with a rank measure, come up with a measure, apply it to the hard polynomial, show that it's high, apply it to the weak circuit that you want to prove lower bound for, show it's small, put the two together to get a lower bound. That's just the entire thing in action, the recipe in action. So this is by Nissan and Witteson. Now I'll tell you why this as is off the shelf will not work for depth 5 already. So let's consider the following polynomial, which I'll call product of inner products polynomial. What is it? You have d many sets. Each set has m variables. Okay, and for every set, the polynomial is defined as product of sum of products. Okay, you can think of it as, so you have, let me say, there are d sets. Each set can be thought of as a vector of variables. And if I were to take inner products of pairs of them, first, second, third, fourth, fifth, sixth, and so on, then the polynomial will look exactly like this. The polynomial will look like this inner part. Then when I take inner products of pairwise vectors, I just product them out. So I take products of those. So that's this entire polynomial. Yeah. Note that this is a depth 4 circuit because there's a trivial plus gate sitting at the top. We always put a trivial plus gate because our circuits are always plus multiply, plus multiply. But if we do that, then it's a depth 4 circuit of very small size. Its size is like m times d or something. But if we look at its matrix, okay, then it's really the permutation matrix. Because if you look at all even sets listing the columns and all the odd sets listing the rows, then a 1 will appear only when exact same variables match up, monomial by monomial. Am I making sense here? So the polynomial is, I'm sure, completely clear. And now look at a monomial listing, labeling the row and labeling a column. This entry is 1 if and only if for every odd variable, a variable coming from the odd set, say ith variable coming from the odd set or kth variable coming from the odd set, if that is present in the monomial labeling the row, then its corresponding matching guy should be present in the monomial listing the column. So like before, for any monomial, there is exactly one entry in this row that is non-zero. Everything else is 0. So it's a permutation matrix again. So what did we just see? There is a depth 4 circuit computing a full rank polynomial. So the recipe is not going to work. So Nisan-Wigderson measure may not be useful in this case. In the last decade, there were very interesting measures defined called shifted partial derivative measures. They were defined by Kayal and used by Gupta, Kayal, Kamath, and Saptarshi to prove really impressive low bound results for depth 4 set multilinear and general circuits. But unfortunately, they seem to stop working at depth 4. There is no formal reason to believe that they will not work for depth 5. Like in Nisan-Wigderson measure, I can show you formally that it will not work for depth 4. But here we don't have any formal reason to believe that it will not work, unfortunately. But we do not know how to make it work. So the results kind of all appear to have happened around 2014. Since then, people have tried in different ways to extend from 4 to 5 for set multilinear, and it hasn't quite worked. So now what do we do? So of course, this is also a BARC talk, so I should not leave out dogs from the talk as well. And so there's a dog. So so partial derivative measure and shifted partial derivative measure seem to not work, but we are using something very similar to partial derivative measure. So it's just we kind of change a few things here and there, and it seems to work. So okay. So I'm going to get into some details, but let's have a check on the time. Maybe another, so how much time is already done and how much is left?
It was scheduled for 16:30, right?
Okay.
So there's an hour left of the scheduled time.
Okay, so what I would suggest right now.
So half hour.
Half hour.
Yeah, sorry, I thought you said 1 hour.
Half hour. Okay, so we have like 2 minutes to go to 4. So 16. So maybe we take a 2-minute break. Yeah, that will be good for everybody, I think. We can then again resume in 2 minutes. Questions are welcome. There's some more cake outside. Oh yeah, but wait, Yakov, wait.
So we're back after the mini break for the final stretch.
Yeah.
Please, Nutan.
Yes. All right. So as I was saying on the previous slide, we have to use sets of different size. So what I'm going to do is I promised you a low bound for IMM, but I'm going to try to prove a low bound for a slightly different polynomial. And tying it back to what Amir was saying, this polynomial is also going to be a polynomial which is eventually computable as an IMM. If you take the entire IMM polynomial and drop out a few edges, then it will give you our polynomial. That will be the polynomial that will be hard, but because it's obtained from IMM, the hardness will continue to hold for IMM as well. It will become clear. This is just a thing for somebody who might get confused already. All right. So what we are going to do is our D sets, which were all equal sized, are now going to be of two different sizes. There are first T sets, which are each of size m, and the D minus T sets, which are of size m to the 1 minus alpha, some size slightly smaller than m. But we are going to choose T in a way that total number of variables here equals total number of variables here. Yeah. So what that will also ensure is that if I look at all the monomials coming from positive sets and all the monomials coming from negative sets, the two sets will be of equal cardinality. And as a result, the matrix that we will form will have as many rows as columns. So it will continue to be a square matrix. We will also ensure that m is sort of a power of 2. This will be useful for some encoding reasons.
So how are this related to the MP and MN sets? Are those, I mean, can I see them in the, or they're big or large, or they're just spread out a little bit everywhere in these?
Yeah, no, I will immediately tell you how they are. Yeah, so let's look at this slide. What's going to happen is that you have 2 to the k elements in each set. So my m is now 2 to the k. And when I choose a certain element here, a certain element here, a certain element here, etc., then that gives rise to the string sigma 1, sigma 2, sigma t. And because these are elements coming from the universe 2 to the k, each can be represented as a binary string. So sigma 1 concat sigma 2 concat sigma t is also a 0, 1 string. And each is in 0, 1 to the k. Now, similarly, the sizes of these sets are going to be 2 to the L. And therefore, every element inside this also is represented by a L-bit vector. And the polynomial is simply this. It's picking together those binary vectors sigma 1, sigma t, which when concatenated are exactly the concatenation of mu1 to mu d minus t. So this is like saying that we are choosing equality string between sigmas and mu's. One more time, maybe. I'm choosing one variable per set between 1 to d, like in IMM. That's exactly the same. In IMM, the way we chose variables depended on if I chose a specific variable from first set, then depending on that, I chose it from the next set and so on and so forth. That is how stitching together happened. Over here, I stitch together across these two sets. I pick certain set of variables from sets of size 2 to the k. And once I pick those, it completely determines what variables I must pick from the rest of the sets so that the monomial will have a non-zero coefficient in the polynomial. And that completely defines my polynomial. It is for this polynomial I will show the hardness. You may wonder what this polynomial has to do with IMM. Because, you know, I started out with IMM, equal size sets and so on and so forth. Well, I'm saying that it is also a polynomial that can be drawn on a graph such that if I take reachabilities of paths and multiply variables out along the paths and add them together, that will result into this polynomial. So in a way, it is a polynomial that can be computed by taking IMM and setting a certain variables to 0 and leaving around certain other variables. So the way to do this would be the way to do this as reachabilities would be that at every layer, I try to remember the unmatched string so far. Okay. Note that though I wrote down the variables in this specific order, it's not so important that all the small sets come after all the large sets. They could even be intermingled because this is commutative setting. So we don't have control over which are big sets and which are small sets. That's not what we control in this setting because variables can come in any order. We are not working over non-commutative setting. But imagine that, so how do I build a graph which in terms of reachabilities of paths will compute exactly this polynomial? It's not so difficult to do it. For example, if k was 3, which is to mean that large sets are represented by bits of length 3. Elements of the large set are represented by bits of length 3, strings of length 3, and elements of the small sets are represented by bits of string length 2. Then I just keep track of whatever has been matched so far. So let's try to trace one path from the source to say this guy and see what all can reach here. For instance, what all can reach here first? All those paths where the green and blue variables have matched, but for a 0. So over here, for instance, 1, 0 got matched with 0, 1, and a 0 stayed unmatched. I think here I ended up doing WW reverse, and in the previous one I said WW, but I'm sorry about that. The picture, yeah, I hope it doesn't confuse you. Over here also we matched 0, 0 with the green set, but one blue 0 left unmatched. What paths reached here? The paths that reach here have one unmatched 1. Over here, for instance, 3 blue ones came and then 2 greens. So 1, 1 remained unmatched. Over here, oh, sorry, I'm doing WW, right, sorry. Over here, I matched 0, 1 with 0, 1, and 1, 0 stayed unmatched. Over here, I matched this 0, 1 with this 0, 1, and this 1 stayed unmatched. So everything that reaches here has one unmatched blue 1. By the same logic, everything that reaches here has one unmatched green 1. It's easy to check that.
Kind of hard to see on this presentation. It's yellow instead of green.
Yeah, I think there's a problem with the projector
Yeah, I
cable.
think so.
Oh, damn.
Messed up.
Wow. Okay.
It's
so
it's not your presentation. Fault.
Over here it's completely green and there it's yellow. I'm sorry. So green and yellow.
Yeah.
I'm happy to say that the virtual experience is perfect in this regard.
Come on, let's leave and yeah. Okay, so this is how you compute this polynomial. I've not been extremely precise here, but I want to just say that this polynomial is kind of hiding. This polynomial is hidden inside an IMM, because IMM would be like blow out this entire graph, take as many variables as the maximum set sizes, and then put all possible edges. And here I just, numb down a few edges and just erase them. That's what.
Just to verify, so in IAM, you would take the number of vertices per layer will be the maximum required, and then every edge becomes one of these formal variables. Is that right?
Yes.
Okay. And so then by this mental exercise, so that means that if you visualize it in this way, then I see that just by identifying variables in the proper way and then zeroing out variables corresponding to edges that I won't use, I can okay.
Yeah, this is called a projection. In fact, what you just did in the mental exercise is known to be a projection. This is like a reduction, notion of reduction in the algebraic world. And what we just saw as a result means that this polynomial that I'm going to show is hard is a projection of IMM. So IMM is at least as hard as this polynomial. Yeah, but anyway. So this is a projection of a IMM which has matrix size is 2 to the k, the largest possible. Okay. So we have mostly everything in place. We have that the variable sizes are set differently now, as opposed to IMM where all set sizes were equal. We are doing this new idea, whatever, and set sizes are slightly different now. And the measure is still the rank measure. And now we want to analyze it for depth 5 circuits. If we are able to analyze it and show that that is small, we are done. That's all that needs to be done now. All right. So in order to do this, we are eventually going to use subadditivity for the outermost summation. So let's forget that for now. Then we are going to probably use submultiplicativity more or less in some situations. But let's focus on this capital F, which is product of sum of products of sums. And note that this the innermost thing, which is like light pink on the slides here and light blue on the slides here, is a model we already analyzed in terms of rank. That Nissan-Wigderson thing I told you about, we've already analyzed this thing. Anyway, so F, capital F here is a product of these FIs, which we kind of know how to handle, more or less. And now I want to claim that it's enough to show that rank of this F is quite small. And how small? This is the maximum rank it can have. And I would like to show that it takes a hit of this much overall. So it doesn't quite achieve full rank. Its rank falls by this amount. And if we are able to show that, then we've achieved our lower bound. Because the rank of the overall thing is S into rank of F. And if it is alleging to compute that hard polynomial, which we showed, which we didn't quite show, but it has full rank, like IMM, then you'll get like full here, which is this quantity. So then the lower bound S will have lower bound of this, which is what we wanted to show, n to the square root d lower bound. So we are good, right? So this is what we need to do. All right. And just to be sure, 2 to the kt can be written in a different way also. This is the number of rows. This is the number of columns in this matrix. And we also set them in a way that number of rows and number of columns is the same. So kt and L into d minus t are the same things. So it's like square root of a square, which is the quantity itself, whatever. So anyway, but why this is interesting is because this is the geometric mean of the number of rows and the columns. And the rank, even if the matrix was not square, then the rank would be min of rows and columns, and that would be upper bounded by the geometric mean. So geometric mean is always an upper bound on the rank, no matter what the size of the matrix is. And we are saying that it will take some amount of hit on the rank, and that amount of hit we will take, we want to show, is substantial to get the lower bound. So this is what we want to prove. And rank of F by submultiplicativity, or rather multiplicativity of, well, I should say submultiplicativity here, right, is rank of F1 times rank of F2 times rank of Fr. And I want to claim that this would be the rank of, this would be the upper bound on the rank of F1 by the geometric mean argument I just mentioned, but it takes some hit. Each of them take enough hit, and then the total hit that they take overall is large. If I'm able to show that, I'm done. Okay. We show that in two cases by dividing it into two case argument. Let's say that there is one, inside this F, there is one Fj which has large degree. See, if it has a large degree component, then already we are looking at a depth 3 circuit, yeah, this pink circuit, which is computing a large degree polynomial. And we already argued earlier that such things are likely to will have small rank. So let me say that. Let me not be so vague. We already saw that the rank is upper bounded by size. Okay. If the size is large, then we already proved the lower bound. I mean, we want to show that the size is large. So if the size is large, nothing to prove. But if not, then the rank is upper bounded by the size, by this, or by the star that I asked you to remember a long time ago. Yeah, but then rank, we are saying, is equal to this times whatever loss we incur. But note that this can now be nicely lower bounded. Why can this be lower bounded? Because we are going to choose, we haven't chosen L, okay, but we are going to choose L, which is going to be at least k by 2. So we get like a k square by 2 there from multiplying k and L. And note pj times qj. These are the, the scaling factors for the sizes that rows and columns of fj have. Well, square root of, yeah, I've written it here. Square root, so the geometric mean of this is at least the average of the two. And we know that we are looking at the case where the degree of fj is large, which then means that this quantity is large, because this is the degree. How many sets of positive size and how many sets of negative size I pick, that is pj and qj inside the polynomial fj. So that's the degree, total degree. And total degree is large is the case we are handling here. So, degree is large. So this thing overall inside, one can check quite easily, turns out to be somewhat like this. And now we already argued that we need to show the loss is large. So by appropriately adjusting these quantities, taking loss to the other side and dividing this quantity by this, we get that loss is large. Okay, so this case is actually simple. You can also think of it vaguely as it follows from Nissan-Wigderson, because when we consider a large degree fj, we are looking at a polynomial of almost square root degree, and it is being computed. Suppose that polynomial was IMM itself, then a depth-3 circuit computing IMM of degree square root d will have a lower bound of n to the square root d. For IMM, it's like really clear, because this is what Nissan-Wigderson showed, that if depth-3 circuit is trying to compute IMM of degree k, then its lower bound is n to the k. So if it was IMM, then this is kind of trivial. We are saying that the new polynomial continues to retain its hardness. So this is kind of easy. The other one is also not very difficult. Okay. So the other case is when fj has small degree. Okay. That's the only case remaining now. I haven't chosen L so far. At this point, I'm going to choose L. Okay. I choose L to be this weird thing. And what is it? Let's just like pass it a bit. It's vaguely 1 minus 1 by, say, 2 square root d, or 10. I'm calling it 10 here, so let's say 10. So it's a quantity that is strictly less than 1 by square root d. It's like a constant less than 1 by square root d. This thing that we subtract from 1 is that much. What we want to say as a result is that if fj is a polynomial that is staring at a degree square root d by 2 polynomial, yeah, it's kind of looking at this and trying to compute it, then at no point will the matrix corresponding to fj will become square. It will be rank deficient for a stupid reason that the number of rows and number of columns will not be equal. One of them will be smaller. And this is where you'll get a loss. And this will happen for every fj. And the losses will multiply and you'll get a lower bound. So that's the thing, and it works. So we have to show that it works. So let's look at the loss. Why is this the loss? Well, this is the number of rows addressed by, 2 to this quantity is the number of rows in the matrix for fj. 2 to the power this is the number of columns. So now I'm going to claim that if I subtract, I just want to say that they are not equal. So if I take the ratio of the two, there's something remaining. So if ratio is non-trivial, that means the subtraction is non-trivial. And the subtraction is non-trivial, again, for a simple reason that this 1 by 10 square root d. So let me just write one more line here. So k times pj minus, what is L? L is k into this 1 minus alpha. Let's call this alpha now. K times 1 minus alpha qj. So let's take k common. You have pj minus qj. There is also this ceiling, this floor. So let's say -1 for that over here. So minus qj overall. So that's also an integer. K times pj minus qj is an integer. The only fractional part here is, what is it? Alpha qj k. And I'm claiming that this integer part cannot cancel this fractional part. So that's it. So this fractional part is at least as much as the loss you have. This is the imbalance between the number of rows and columns, at least. It could be worse, which is even better for us. And that's it. So you get a loss of this per term, and putting it together, believe me, gives this sort of a low. It's only about setting parameters. So that's it. Yeah. Oh, yes. So overall, this is what we did right now. I think I'm done.
You got some applause emojis from Zoom as well.
Yeah, we can see that.
Thanks, Amir. So I have like sketches for other things, but I think it's too much now. Stop with the open questions. They're the same from the previous one.
Go back to the open questions. Just.
Oh yeah, sorry. Oh, Radu, you are in two. Multiple Radus here.
Thank you so much, Nutan. This was fantastic. We already had ample opportunities to ask and did ask during the talk. I don't know if there are any final questions before we wrap up. I mean, we should also cut Nutan some slack. I guess she worked hard now for 2.5 hours. I mean, I don't know. So I guess one very speculative question, but the natural one. I mean, you're right at the boundary for depth 3, where like miraculous things would happen if you push this further. Do you believe that, you know, just working a little bit harder, you'll separate VP and VNP, or like you believe that you're up to like foundational obstacles somehow?
I think we have obstacles. So we were thinking about this quite a bit. And at least what we are able to argue now, more or less, is that our techniques alone will not be enough to push this any further, kind of at depth 3, for instance. So there seems to be like a bottleneck. If we are just using this argument that we use these set sizes to balance out things, and we analyze the formula in this specific way that I was telling you about, then we can kind of show now that it will not be able to push the lower bound further. But there may be variants, there may be a harder polynomial for which we could do this. So I'm not saying there is no hope, but at least exactly same recipe with tweaks may not work.
Okay, thanks.
Can I ask something?
Yeah.
just something you mentioned before, which I might have misunderstood, but this IMM polynomial, did you say that it was in the class VP?
Yes.
All right.
So the question being asked is IMM in VP? So one easy way to see this is like counting the number of S2T paths has polynomial time algorithm. Well, I don't know whether I'm, huh? In a DAG, of course, DAG, layered DAG. This may be one way to see the counting version, but
right. So there is, so that means that there is no, we can't prove anything harder for this particular polynomial.
That's right. Yeah. So if we work with IMM alone, then there is no hope of separating VP from VNP. Right. Because it's not a VNP hard or some such polynomial. It itself is quite easy to compute.
Yeah. Are there any canonical examples of like this is a VNP polynomials that people look at?
The most well studied one is the permanent.
All right.
Permanent polynomial, and one doesn't know how to push these lower bounds for that. Of course, our lower bounds will mean something for the permanent as well, some weak sort of lower bounds, but not the kind which will separate VP from VNP.
The same lower bound holds for the permanent.
Degree has to be small in our entire argument. So for permanent, degree is very large. So what will happen is the lower bound will not scale with the degree for permanent. I'm not sure whether I answered your question satisfactorily.
But are there any other like natural examples of polynomials in VNP which have these small degrees? Or?
Yeah, so the other result, that's cubic result I mentioned, that was the previous one that was best known. That used something called, they are also called Nissan-Wigderson polynomials, but for a totally different reason, Nissan-Wigderson, because it's like the Nissan-Wigderson pseudorandom generator. And it's from there that in algebraic complexity, people have come up with polynomials where the two parameters are separate. In permanent, what happens is the degree is dependent on the number of variables. If the number of variables is n square, the degree is n, square root of that. So in that other polynomial, in IMM, we are able to sort of decouple them, d and n. In this other Nissan-Wigderson polynomial also, there are multiple parameters we can play around with. So degree and the number of variables can be decoupled there as well. So that's a candidate polynomial perhaps.
Okay, thank you so much, Nutan, for a wonderful talk.
Thank you so much. Yeah, thanks for having me for this seminar.